Welcome back, everybody. Mr. Johnson here with you once again. This is Lecture 12, Section 4.8, Stoichiometry involving excess and or limiting reactants. If we take a peek at this warm-up, which is a great analogy for limiting reactants in chemistry, we're looking at a table that tells us what it takes to make a sundae: ice cream, syrup, and cherries, the amount that is on hand in a sundae shop. And wouldn't it be nice if we were eating sundaes together right now instead of you watching me once again on YouTube? Looks like there's 6 scoops of ice cream on hand, 200 milliliters of syrup, and 475 cherries. And the recipe that it takes to make a sundae, which has to be stuck to, cannot be altered, is 1 scoop of ice cream, 50 milliliters of syrup, and 1 cherry on top. The idea of that recipe being unalterable is analogous to, in a chemical reaction, that the ratio in which things react and are produced, the coefficients are fixed. That can't change. That's a physical law of nature. So if we look at the number of items on hand, we can ask ourselves, well, if the other 2 ingredients were in excess, if there was plenty of the other 2 ingredients, how many sundaes could we make? Looks like from 6 scoops of ice cream, you could make 6 sundaes, for it takes 1 scoop per sundae. From 200 milliliters of chocolate, were there plenty of ice cream and plenty of cherries, you could only make 4 sundaes, because 200 over 50 is 4. And from 475 cherries, with 1 cherry on top of each sundae, you could make 475 sundaes. So it looks like the chocolate syrup would limit how many sundaes could be made, and whatever ingredient, or in chemistry, whatever reactant limits how much product can be made, or in this case sundaes, is the limiting reactant, or limiting ingredient. And the other 2 in this case, the ice cream and the cherries, would be referred to or considered as ingredients or reactants in excess. There's more of them than are needed, and there will be some of those 2 ingredients left over after the recipe has been made to completion or the reaction has proceeded to completion. So what that warm-up was about, or what that analogy is telling us, is that we need to look at all the reactants, the amounts of all the reactants, to figure out how much product will be formed. Because if we look at just one reactant, we may not be able to form as much product as we think we can. So set that aside for a moment, that analogy for a moment, and let's look at other reasons why there may not be as much product form as we think, besides this whole limiting reactant concept. Well, one of those reasons might be because the reactant that's provided is not completely pure. We assume that if you're given 10 grams of sodium, it's pure sodium, but maybe there's some impurities in there. So there isn't, in fact, 10 grams of sodium, and you don't produce all of the product that you think you would from 10 grams. It may also be that a reactant may not be totally consumed in a reaction. That for some reason, all of those particles don't get collided against or don't react for some reason. Even if the reactant's pure, maybe not all those reactant particles react, and therefore we don't produce as much product as we think. Maybe there's some side reactions happening that we don't know about. There's an impurity in the water because it wasn't distilled water that's reacting with one reactant, and therefore the product that we think would be made is not made to the extent we would predict. And it's possible that not all reactants, just like we saw in the warm-up, are combined in the stoichiometric ratios that the coefficients in the balanced equation require. Therefore, you might run out of one reactant before you run out of another, and you don't produce as much product. So those are all things to consider as you're predicting how much product will be formed, and realize that it may not always be as much as you think. And it's that last statement I just made, the fact that the reactants may not be combined in the same stoichiometric quantities as the coefficients require, that is what the remainder of this lecture is primarily about. The fact that oftentimes we will have one reactant that is limiting and one that's in excess, and how do we deal with that mathematically and conceptually. I'm going to invite you to do this quick check on your own, and then pause the video and come back, and after you're done, see how you did. But before I ask you to do that, I want to remind you once again that the reactant that is totally consumed when a reaction is completed is called the limiting reactant. And that is the reactant that determines how much product will be formed. It's the reactant that remains once the limiting reactant is completely consumed that is called the excess reactant. The reactant that there's more of than will be consumed, that there's some of left over, is the excess reactant. Take a moment to do the quick check, pause the video, come back and see how you did. So what I did is, looking at the equation here, the 2 COs to 1 O2, is I crossed out 2 COs and 1 O2 and said, all right, well, 2 COs react, that would be 1 O2. Then I crossed out another 2 COs and another O2, and I've run out of CO, so the reaction can't proceed anymore. And what we're left with, as we can see, is a single O2 molecule. And if two COs and one O2 make two CO2s, if that happens at a magnitude of 2, if that happens twice, then we're going to get 4 CO2 molecules. It looks like there's one O2 in excess left over. So CO is our limiting reactant, O2 is our reactant in excess, and in this case there'd be one O2 molecule left over. So I've scrolled down page 255 of my ebook now, and I'm looking at this sample problem, which is the first limiting in excess problem that we'll be solving together. It asks, what volume of hydrogen gas measured at STP is produced when 8 grams of lithium metal is reacted with 10 grams of water? And then it asks, what mass of the excess reactant remains once the reaction is complete? Now it tells us this is a limiting in excess stoichiometry problem, but if it hadn't told us that and you were just confronting this in a more typical situation, you would know it's limiting or excess if the amounts of 2 or more reactants are given to you. Again, how you'll know if a problem is a limiting or an excess reactant problem is if there's the amounts of 2 or more reactants given to you. So the first step, once you've got the balanced equation, is to convert the masses of both reactants, not yet knowing which one's limiting, into moles. And we can see that being done here. 1.2 moles of lithium, 0.556 moles of water. Because the reactants are reacting in a 2-to-2 or a 1-to-1 ratio, you could simply compare these two mole numbers, and whichever is lesser, in this case water, is telling us that water is the limiting reactant. But that's not always going to be the case if the coefficients are the same. So we're going to flip the page and see how you will solve a problem where you don't have the same coefficients, or frankly how you can solve all limiting reactant problems even if the coefficients are the same, which is what I recommend. So same first step, take the mass of both reactants, convert to moles by dividing by molar mass, use the mole ratio between the reactant and the product you're trying to find out the amount of. In this case, that's hydrogen, because that's what the problem's asking us about. It's important that you, using both reactants, find the amount of the same product to compare those numbers, because whichever of those is lesser, again, tells you which is the limiting reactant. So we're finding the volume of hydrogen from both reactants. And from water, we see that it's 6.22 liters of gas at STP, whereas from lithium, it's 13 liters. Also justifying, like we knew from earlier, that water is the limiting reactant because it produces fewer liters of the same product of hydrogen gas. Once we know what the limiting reactant is, we can solve all sorts of other problems if we're asked to in that same problem. We could figure out the amounts of the other products that are formed, or the amount of the other reactant that actually reacts. And because this one asked us to find how much of the reactant in excess is remaining, what we will first do is find the amount of the reactant in excess that actually reacts, and then subtract that from the mass that we're given. So we take the 10 grams of water, the mass of the limiting reactant, and convert it to the mass of lithium that actually is used, which is 3.83 grams, using stoichiometry. And then we subtract the amount that we are starting with, the 8 grams, from the amount that actually reacts, 3.83, and find that there's 4.2 grams of lithium remaining. So I've scrolled down, I'm on the same page, looking at practice problem 2. I'll read it to you, recommend that you try to solve it on your own. Pause the video and come back and see how your solution compares to mine. So we've got an acid spill that contains 12 grams of pure sulfuric acid that's neutralized by 80 grams of sodium bicarbonate. Sounds like it's a neutralization reaction. What volume of water is formed? And like the last problem, what mass of the excess reactant is left over? So this is very similar to our sample problem. So the first thing you'll need to do is write out the formulas of the reactants, predict the products, balance the equation, and then do the kind of work we just saw again in the sample problem. Consider pausing the video, trying this on your own, and come back in a moment again and see how you did. All right, let's see what we got here. So here's sulfuric acid. Remember, if it's icky, you ate it, so there'd be sulfate in the acid, and 2 hydrogens paired with that, since sulfate's a 2-. All acids are dissolved in water, so there's AQ. Sodium hydrogen carbonate, NaHCO3. It's an ionic substance, which are almost always solids at room temperature, so I've got an S there. This is a double replacement reaction, or a neutralization reaction, because this is actually a base, which you might not have known. So sodium and hydrogen switch places to give us sodium sulfate, and what would be carbonic acid. When hydrogen combines with HCO3, it's H2CO3. But remember, carbonic acid is one of those substances that immediately decomposes into smaller substances, CO2 and H2O. So the other product is carbon dioxide and water. All right, so we take the masses of both reactants, 12 grams of sulfuric acid, 80 grams of water, and figure out what the volume of water would be from each of those reactants. Remembering that whichever reactant produces lesser of the same product is the limiting reactant. So I divide them both by moles, use the mole ratio to convert to moles of water, multiply by water's molar mass to get mass, and then because I'm asked for volume, and this is not a gas at STP, and I can't use 22.4, I'm using the density in the last step to convert to milliliters, which mathematically doesn't do anything because of the ones, but it's important for unit cancellation to have it there. And notice I put grams on the bottom so it cancels, and milliliters on the top. So 4.4 milliliters is less than 17.2, which means that sulfuric acid is limiting, and the amount of water, which is limited by sulfuric acid that will be produced, is 4.40 milliliters. Like we learned in the sample problem, you can then use the limiting reactant to figure out anything else going on. So the second part of the problem is to use the 12 grams of sulfuric acid to figure out the mass of sodium hydrogen carbonate that will actually react. So that's the work there. And I find that only 20.6 grams of sodium hydrogen carbonate reacts from 12 grams of sulfuric acid. So if we take the 80 grams that we were given, subtract from it 20.6, final answer of 59.4 grams of sodium hydrogen carbonate. Well done, folks. Whew, that was a lot of writing. All right, so I flipped the page. I'm on 257 of the ebook now, looking at this section titled Percentage Purity. And this is telling us, as we might imagine, that the percentage purity by mass of a sample is equal to the ratio of the mass of the pure chemical divided by the mass of the impure sample. So if we, for example, had 10 grams of a sample that had sodium in it and some impurities, that'd be the 10 grams of impure sample on the bottom. And if we knew 8 grams of it was pure sodium, 8 over 10, of course, would be 80%. So it's the mass of the pure component of the chemical divided by the mass of the impure. There's a couple quick check problems down below that you could do if you want, but I'm not going to solve this with you right now. All right, I've flipped a couple of pages. I'm now on 259 of the ebook, looking at this section titled Percentage Yield or Incomplete Reactions. We already know that in some reactions, there might be one reactant in excess and one that's limiting, and that the limiting reactant will determine how much product is made. But the amount of product we calculate is a theoretical amount. That's how much product in theory will be made if all of the reactants react completely, if the reaction goes to completion. And that's what this section is talking about, is that not all reactions, in fact, go to completion. The limiting reactant won't always get used up entirely, and we won't produce as much product as we think. So something that's common to do in lab is to cause a reaction to occur, to determine how much product we get, and compare it to how much theoretically we think we would have gotten from the stoichiometry that predicts that. And that's a percentage yield calculation. Percentage yield is the amount of product obtained, the amount you actually obtain experimentally, divided by the amount you would expect. And that amount you expect, there should be a divided by line in there. Now it's there. Typically comes either from a value that's given to you or comes from stoichiometry. Because stoichiometry predicts how much you'll get, but doesn't assure it. Well, the amount that is predicted is often called the theoretical yield as well. So another thing we could say is percentage yield is the experimental yield divided by the theoretical yield times 100. So we're about to flip our page, solve one more problem with you, and that will be the end of our 12th lecture. So we're looking at practice problem 1 here on page 260 of our ebook. And the problem reads that a chunk of zinc metal reacts with an excess of hydrochloric acid solution. It's looking like a single replacement reaction, by the way. What is the percentage yield if a 7.23 gram piece of zinc produces 2.16 liters of hydrogen gas at STP? And then it reminds us to begin with a balanced equation. So what we're going to do in this problem, after we write our balanced equation, is to take the mass of the zinc and, using stoichiometry, calculate how much hydrogen gas in theory will be produced. That will be our theoretical yield coming from stoichiometry. We'll then compare that to how much was produced, this 2.16 liters, in that percentage yield formula you just saw, and that'll be our final answer. So I'm going to take you to the whiteboard once again to solve this problem. thing I want to acknowledge that I didn't mention a moment ago is that the HCl is in excess. Of course, that was in the problem. And that whenever a reactant is in excess, we know that there's more of it than is needed to react, and we just ignore it in terms of the stoichiometry. So I've got solid zinc reacting with hydrochloric acid. Remember, hydraulics for a smooth ride, which is how I knew chloride was in there. So I've got HClAq. And I already mentioned this is a single replacement reaction, so we're going to imagine zinc replacing hydrogen. If we're given a problem like this where it says there's a reaction, assume that zinc will replace hydrogen. But if this were a predicting products problem, we'd ask ourselves, is zinc higher than hydrogen on the activity series? Is zinc higher than hydrogen on the activity series? And in fact it is, which is further proof of this being a reaction. So zinc will pair with chloride. Zinc's a 2+, chloride's a 1-, we get CnCl2, and that is soluble. And then we get hydrogen gas as our other product, H2 gas. And when we balance it, we need to put a 2 in front of HCl. So we'll now do our stoichiometry. We're going to take 7.23 grams of zinc. And first step is always to convert mass to moles. So I put 1 mole of zinc on top, and its molar mass of 65.39 grams on the bottom. I'm going to hydrogen gas because I was given the amount of hydrogen gas actually produced. And again, my goal is to figure out how much will theoretically be produced from stoichiometry. For every mole of zinc that reacts, I produce 1 mole of hydrogen gas. And then because this is a gas at STP, I can use 22.4 liters per mole. So I know that 1 mole of H2 is 22.4 liters of H2. So I plug all of that into my calculator. 2.48 liters as the theoretical yield. That is how much hydrogen gas would be produced if all of zinc reacts and the reaction goes to completion. But we know that only 2.16 liters was produced. So we'll use the percent yield formula. That's the experimental yield, how much was actually produced compared to how much in theory should have been produced. So that's going to be our 2.16 liters divided by 2.48 liters times 100, and we get, and that concludes lecture 12. Mr. Johnson signing off, and you know what they say, if you can't say anything nice, maybe don't say it at all.